Okay, so now we'll see the combined tutorial of the week 7 and 8. So in the week 7 we discussed about the observability, and in the week 8 we discussed about the state estimator design. So since both the concepts are pretty much related, so we'll go with the combined tutorial. So these topics would be covered for solving the numericals. So the first three problems are basically from the week 7, and the next three problems are basically you can relate with the week 8. So from the week 7 we will focus on to the observability under the state feedback. So one of the concepts we had studied during the controllability week, that once you have designed a state feedback controller, then the controllability is invariant, but we cannot ensure the observability under the state feedback. So we will see one of the problem on that aspect. Second, we shall see the duality for time varying systems. For the LTI system, we had seen a detailed proof about the duality, but we have left this question unanswered at that time, that if there exists any duality for the time varying case similar to the LTI case. The third problem is about the minimal realization, where we will try to correlate the concepts of controllability and observability with the with the many realizations. So the fourth, fifth, and sixth problems are basically about the output feedback, observer design, and the unknown input observer design. In the first problem, we are considering the state equation. X dot is equal to ax plus bu, y is equal to cx, where a, b, c matrices are given here. So this problem was taken from the example 8.1 of one of the references mentioned on the course page. So first we need to investigate about the observability of the system. Second, we shall design the state feedback of this form, which is r minus kx, where k is a vector composed of k1 and k2. So we need to investigate whether the system is observable under this state feedback for all k1 and k2. Okay. So the first part is pretty much straightforward, that you compute the observability matrix given the A and C matrices, and finally check the rank of that observability matrix. So here it is a full rank matrix, so the system is observable, but the interesting part is to see whether the observability is invariant under this state feedback. So let's put this controller into the state space system. In that case, the closed loop system matrix would be given by, we denoted here by A subscript C is equal to A minus BK. So substituting the corresponding values of A, B, and taking K1, K2 as the parameters, so we computed the observability of the closed loop system in terms of K1 and K2. Now if we put K1 is equal to 3 here and K2 is equal to 1 here, so from here we would get, by putting K1 is equal to 3 we will get 1, and putting K2 is equal to 1 we will get 2. So this is straightforward to see that the rank of this observability matrix is not 2 but 1, meaning to say that the system is not observable under the state feedback. The second problem discusses about the duality. So given the pair A and B, which is time varying, so we need to show that the controllability of this pair is equivalent to the observability of the pair which is minus A transpose and B transpose. Okay. Now if you recall the result for the LTI system, if A and B are time invariant, then let's say the controllability of the pair A comma B is equivalent to the observability of the pair A transpose B transpose. Okay, but here we have a slight change. Here we are having the negative sign, so we need to investigate whether we can have some duality in for the time varying case. So to solve this problem, we consider two systems. The first system is x dot is equal to ATX plus BTU. Another system is where we have replaced the A matrix by minus A transpose, and the output matrix we are taking as B transpose. Right? We have deliberately write these state space equation into these forms because we will investigate the controllability of this system, and for investigating the controllability we only need the AB pair. Now for observability we only need the pair the state matrix and the output matrix, so we have not considered any input term here. Corresponding to these two systems, we are defining two important parameters which are required to solve these time varying systems. First is the fundamental matrix, which we have denoted by X for the system 1, and the fundamental matrix denoted by X1 for the system 2. Similarly, this phi is the state transition matrix for the system 1 and phi 1 is the state transition matrix for the system 2. These are the two important parameters which we have discussed in the first week when we had seen the solution of the time varying systems. Now we will recall first of all how we have defined the controllability and the observability in terms of the Gramians. So these concepts are basically related to the week 3 and week 7, where we have shown that the controllability of the pair A comma B is equivalent to the full rank of this Gramian, which we have defined as the controllability Gramian. So here we are taking directly the state transition matrices, this phi, and the B and B transpose remain as it is of the input distribution matrix. For the observability, since these are the state and the output matrices, we have directly written the Gramian in terms of these pair, which is supposed to be full rank if we want to ensure the observability of this pair. Okay. Now the logical idea behind the proof is, if we are able to show that WC is actually equal to WO, and if we ensure that this is a full rank, it is necessary that this would also be a full rank. Okay, so this WC we have defined for the system 1 and WO we have defined for the system 2. So we only need to show the equivalence of this WC and WO. Now if we pay attention to onto the right hand side, the terms which are appearing in at the middle of this integrand remains the same. Okay, the difference lies only in the state transition matrices. So the next idea is, if we are able to show some kind of relationship between this phi or the state transition matrix of the system 1 and that of the system 2, then we can directly show that WC is actually equal to WO. Okay, now with a clear look, we only need to show that phi t1 comma tau should be equal to phi 1 tau comma t naught transpose. Similarly here. Okay, so now to show the equivalence between this WC and WO, we need to show the equivalence of the state transition matrix, and the solution of the state transition matrix basically hinges upon the fundamental matrix. Okay, so let's see if there is any relationship between the fundamental matrices of both the systems, and then we will come directly onto the state transition matrix. So let xt be the fundamental matrix of this system. We only need to consider the homogeneous system. Then we know that the fundamental matrix actually satisfy this equation. So we can write the derivative of capital X is equal to A times capital X. Another property which we had also seen during week 1, that X inverse T and X of T is actually equal to the identity, and X is a non-singular matrix. So taking the derivative both sides of this equation, which is this one, we can and further simplifying, you will end up to this relationship where it says the derivative of the inverse of the fundamental matrix is actually equal to minus inverse of X and A, right? So this is a key equation and we will put it as equation 1. Now consider the second system whose fundamental matrix was x1 and the state matrix was minus A transpose. Now similarly, uh, what we had seen in the previous slide, that x1 again would satisfy this state equation and we would obtain directly this equation as equation number 2. Now if you compare both these equations 1 and 2, you would see that the A matrix is at the same place, and now x1 transpose actually become equal to x inverse. Okay, now under this condition both the system would be the same. Similarly, if I take the inverse of the x1 transpose, it would become equal to x. You just need to take the inverse both sides. Okay, so you will get this equation. So both the systems are related by the some relationship between their fundamental matrix. So now let's see the state transition matrix, which we had seen in the week 1 as well, is given by the multiplication of the matrix X and its inverse at some time tau. Okay, this is how we define this phi t comma tau. Now for this system we can write the phi 1 as again this one. Now here x1 we have replaced from the equation 3 what we have obtained in the previous slide. Further simplifying it in terms of the only x, we obtain that the transpose of the state transition matrix of the second system is actually equal to the state transition matrix of the first system with the time reversal. Okay, phi 1 transpose t comma tau is equal to phi tau comma t. So this is again a key equation which we will going to use it later to obtain the result. So let's proceed again with this equation 4. So we had seen that the pair AB is controllable if this matrix is a full rank. So again we are using one of the properties of the state transition matrix, that if I take some time t naught in between t1 and tau, then I can write this phi t1 comma tau as the multiplication of two phi's as t1 comma t naught and t naught comma tau. Okay. Now substituting this into this WC and simplifying, we can take a pre-multiplying factor phi t1 comma t naught as the common part, and the post-multiplying factor is phi transpose t1 comma t naught. Now from the property of the state transition matrix that it should be non-singular, so for WC to have a full rank, this term should be positive definite, or should be in fact definite. Okay, should only be definite. Definite in the sense that this matrix should be non-singular, which we have defined here as eta, this common part eta. Okay. Now coming on to the observability Gramian of this pair, and using the relationship which we had obtained in the equation 4, I can replace all these phi 1 by this phi with the time reversal, of course. So directly by replacing the phi 1 by all phi's, we obtain this W, which is nothing but equal to eta actually. So here we had shown that the observability matrix of the second system is actually equal to the controllability Gramian of the first system. Okay, so this established the duality, which you would realize that which is slightly different from the LTI case. The third problem is about the minimal realization. So we are given some transfer function which is a single input single output transfer function, which is s plus 1 over s square plus 2. So here we want to find three realizations. First one should be unobservable but controllable. Second, uncontrollable but observable. And third, a minimal realization, which is equivalent to saying that that realization is both controllable and observable. So here we will going to use directly this MATLAB command to obtain the realization, which you can also compute by going through the procedure defined in the slides. So the controllability or the full rank of the controllability matrix and the observability matrix ensures that the system is controllable and observable both. So to obtain the unobservable realization, what we have done here, so in this transfer function we have added one polynomial factor both in the numerator and in the denominator. Okay, so opening this polynomial we would obtain this one. Now for this transfer function we obtain directly the controllable canonical realization in form of this ABC matrices, and if you compute the controllability of this matrix, it is of full rank, but it is unobservable because the rank of the observability matrix of the pair A comma C is only 2. Okay, so this realization is an unobservable realization. Why? One insight of this one is that because we have added a common factor both in the numerator and the polynomial, which if we are seeing only the external signals, that is to say input and output signal, won't be the transfer function would not be able to capture it. The second part we could solve straightforwardly by taking the dual form of the system A, that is replacing the A matrix by its A transpose, B matrix by the transpose of the output matrix of the first system of the first equation, and the output matrix by the transpose of the input matrix of the first system. So these are the matrices what we have obtained. Now if we compute the observability or the rank of the observability, then it shows that this realization is observable, but again it is not controllable. And this is what implicitly the concept of duality says. Now lastly is the realization which is supposed to be minimal, and we had seen detailed proof that that realization should be both controllable and observable. Now one of the inherent meaning of this is that both the numerator polynomial and the denominator polynomials are co-prime. That is, there are no common factors in those polynomials. Okay, so now directly writing or computing the ABC matrices, we obtain these ones, for which you can compute the rank of the controllability matrix and the observability matrix, which is supposed to be 2. So this realization ABC is the minimal realization. Okay, and this minimal realization basically in terms of the dimension of the vectors, the state vector. In the next problem, we want to design a feedback controller, but here there is a slight difference. So let's see first. So given this simple system, which is a second order system with 2 states and 1 input, which is acting only onto the second state dynamics. So here we want to check whether the system can be stabilized by a static output feedback under these 2 scenarios. So here we are considering 2 different scenarios in which our y1 is x1, so we are taking x1 as a direct measurement, and in the second case we are only measuring x2 into the output. So if you recall the concepts of the controllability we had discussed earlier, I can directly obtain the ABC matrices of these two equations. Now if you check the controllability of the pair A comma B, it would be controllable. Okay, it would be controllable. Now what we want to see, that whatever the concept we had studied about the controllability, is there some relationship between the controller state feedback or the output feedback controller design? Because do not forget that the concept of controllability we had discussed is only about the state. So basically we should refer it as the state controllability. Okay, so let's see. So the AB matrix for the system is given by these matrices, and we want to apply this feedback, which is given by u is equal to ky1, and y1 is nothing but c1x, and c1 is 1 0, where I am taking actually the state 1, the first state. So if I see the actual control law, it is u is equal to kx1. Okay, meaning to say I am feeding only the first state and want to see whether the system can be stabilized by feeding only one state or only the first state. So if we check the state matrix of the closed loop system, I will obtain this as A plus B KC1, and substituting the value of A, B, K and C1. Basically we want to analyze for K. So after substituting all these matrices, we obtain the state matrix as this one. So we can analyze that for what values of K this system can be analyzed by computing the eigenvalues of this matrix. So which basically aims to solve this quadratic equation for the lambdas. Now from this equation you would see if K becomes equal to 1, right? K becomes equal to 1, then the eigenvalues would be a conjugate pair of imaginary eigenvalues, meaning to say that the system would be oscillatory. Now if K becomes equal to 1, then we would have a double integrator, meaning to say that the system is again unstable, and if K is greater than 1, then all the eigenvalues would be positive. That is on the right hand side. So for all the values of K, using this control law as u is equal to kx1 would never give you a stable system. Okay, that is to say the system cannot be stabilized by this output feedback. Now consider the second case, where instead of feeding back the state 1 or the first state, we want to feed back the second state. Okay, so let's see. So now the control law would become u is equal to kx2 finally, because the C matrix or the C vector has been changed to 0 1. So here we should have x. Okay, so for this case the closed loop matrix would be given by this one, A plus B KC2, and in terms of K, this would be a parameterized state matrix. Now computing the eigenvalues, we obtain this one, and you would see that any choice of negative values of K, these eigenvalues would be onto the left hand side. Okay, so this means that if I feed back both the states, so I know from the controllability property of the pair A comma B, the system can be stabilized. Okay, but now if I see that instead of feeding back both the states, if I feed back the first states, the system can never be stabilized. But by feeding the second states, we see that the system can be stabilized for the negative values of K. Right? So the concepts of the state controllability, what we had discussed, is basically different from the what we are seeing in this numerical. In the problem 5, we have some armature controlled DC servo motor whose ABC matrices are given by these values. Okay, so here your C would be a vector containing only uh, first non-zero element. The other two elements would be 0 of the C matrix. So the definitions of the states and inputs are given here. We want to design a full order state observer with eigenvalues placed at -1, -2 and -3. Okay, so the idea of designing the observer originated from when we want to when we want to design a state feedback controller and we do not have the direct measurement of all the states. So instead of using this state x1, we want to use the complete state. So this is what we had seen in the previous example, that somehow if we are able to design an observer for estimating both the states, then we know from the controllability property of the pair the system can be stabilized. So here again we have a direct measurement of only one of the states but not all of the states. So we want to design a full order state observer by placing the eigenvalues onto these values. So here we would, so in the lectures we had discussed two methods. First is the eigenvalue assignment method, which is basically the give you the Leuenberger observer. Second is the based on the Lyapunov equation. So here we will go through the steps of computing the observer matrices by using that method, and finally we will see some simulation results. So the first step in this method is we want to select an arbitrary F matrix whose eigenvalues are actually located at the desired values. Now the second step, we select arbitrary L vector such that the pair F comma L is controllable. So we have selected this L vector and this pair FL is also controllable. Now the third step is computing the T matrix, which is obtained by solving this Lyapunov equation, and we have used the Lyap command, so this command in MATLAB, to obtain this T matrix. Now the observer, if you recall, was given by this state equation z dot is equal to fz plus tbu plus ly, and the state estimate is given by the inverse of that T matrix times z of t. So substituting the matrix, the computed matrices by using the steps we had seen earlier. Now we can go directly to the simulations. If I place this observer to estimate the actual states. So here we see that the blue curves are the actual states and the states which are drawn in the green color are the estimates. So only during the the transient periods, the state value do not match, but when it reaches to the steady state, both the states overlap, meaning to say that whatever the observer we have designed is actually able to estimate all the states. So this is the last problem where we want to design the unknown input observer. So we are considering a system where now we have added a disturbance term with its distribution matrix E. So this A, B, E, C values are given here. So here D is the disturbance, which is a sinusoidal term, and it is not, and this variable is not directly measurable. Okay, so here, so this problem was also this numerical problem was given by in one of the paper appeared in the Transactions on Automatic Control in 92. Here we want to design two observers. So in the first part we will design the Leuenberger observer, which we have designed using the eigenvalue assignment technique, and the second we will design the unknown input observer. So if you recall, in the Leuenberger observer design technique, we require, or in fact in both the observers, we would be taking only the input and output variable as the input signals to the observer, because we do not have any information of the, or we are not supplying any information of the disturbance variable to the observer. Okay, and finally we will compare both the responses obtained from both the observers. Okay, so let's see. So this was the observer equation which we had discussed on slide number 9 to 10, where x hat is the state estimate, y hat is the output estimate, and L is the gain vector which is supposed to be designed. So if you recall that the error dynamics were given by E dot is equal to A minus L times CE, where we can compute directly this L matrix if the observability of this pair A comma C is satisfied. Okay? So we have used the MATLAB command place to place the eigenvalues onto the left hand side, and we have computed this L matrix. Now for simulations, we have taken the initial conditions at the origin. So if we see the response of the system and the observer, we see that not only at the transient period but also at the steady state period, the state estimation error do not go to zero, and it is because that we have not supplied the information of the disturbance to the observer, right? Now we shall see that if this problem can be overcome by designing the unknown input observer. So the detailed designing steps were given on to the lecture slide number 44. So here we will quickly go through all the steps to compute the relevant matrices, and then finally we will see the simulation results. So the first condition, which was basically the existence of the UIO, and from there we gave a special solution of this H matrix. So if we check the rank condition of C and CE, it is equal to 1. So a UIO exists, and this H is a special solution which we have computed with this matrix. So the rest of the matrices were straightforward to compute, the T matrix and the A1 matrix, once we have computed the H matrix from the first step. Now the third step, where in the third step we need to investigate the observability of the pair C and A1, and A1 we had computed from this second step. So here we see that this pair is observable, so we do not actually need to go through the steps 4 to 8, because in the 4 to 8 steps we basically discussed that if this pair is detectable, then how you can compute this matrix K1. Okay, but here since the pair is observable, we can directly compute the matrix K1 using the MATLAB command place. Okay, so here we have placed the eigenvalues at -1, -2 and -3, and we have obtained this K1 matrix. So from the K1 matrix we have obtained F matrix, which is supposed to be a Hurwitz matrix, so you can compute the eigenvalues, and from K1 and H and F we have finally compute the K matrix. Okay, now putting all those matrices into the observer, F should be a stable matrix, T we have already computed, B is the output, the input matrix, and K is the an output injected term, and in X hat ZT plus HYT. Okay, again here we are taking the initial conditions of the observer at 0, 0, 0, meaning to say, so the state of the observer is basically Z, and the output of the observer is the X hat. Okay, now if we see the simulation results, that although we have not supplied the information of the disturbance to the observer, still the observer is able to estimate the actual value of the states. Okay, so this is the significance of the unknown input observer, because we have eliminated the effect of the unknown disturbance onto the observer, which was pretty much visible when we had discussed the Leuenberger observer. Okay.